Audience, I'm going to make the risky assumption that we're not going to have another snow day this week. So, what I was going to talk about was something slightly, sort of like a pair, things that went quite well together, but were like two slightly shorter lectures. So remember yesterday we were going to have two lectures. So rather than kind of do something truncated today, I'm going to sort of do a slightly more full topic, and then tomorrow I think there's going to be two, one after the other, but probably not like packed to the brim, right? So, gosh, it feels like the room is echoing. It's really unnerving. So we saw the black string when we were talking about Kaluza-Klein black holes, and I'd kind of like to carry on that theme and just discuss what can happen with black solutions in higher dimensions. So in 4 dimensions, at least in asymptotically flat space-time, we can only have a black hole. We can't sort of have a black plane or hyperbolic horizon. And we sort of saw that when I was writing down the Schwarzschild potential when we had a cosmological constant. So remember, this potential here went to a sort of kappa minus 2gm over r minus lambda over 3r squared. So for our signature to be right, this thing has to be positive. And so we saw that if lambda was either 0 or positive, kappa had to be 1. And that's sort of indicative. Kappa's the curvature of this space here that's surrounding the black hole at constant distance from the black hole. So if it were planar, kappa would be 0, because then that would just be a sort of 2-plane. But if lambda is negative, then we have more possibilities. So I'm kind of not going to particularly go there at the moment. I just really want to say that I'm making the point that in 4 dimensions, we have to have a black hole. However, once we go in higher dimensions, we've already seen that's not the case, because here we've got this as a solution, a Ricci flat solution, so it's an Einstein manifold, and we have the interpretation of it as a black string. So it seems like once we go to higher dimensions, we have more possibilities for black hole-y type solutions. And you can sort of see that if I were to take that dz squared and turn it into a dzn squared, a sort of flat space, that would also be a solution to the Einstein equation. So I can add as many sort of extra dimensions as I want to sort of end up with, black string, black membrane, etc., etc. Okay, so how might we find out what these solutions are? Well, we have to solve the Einstein equation. So I'm just going to give a sort of schematic. First of all, let's just remember what we did when we were looking for that kink, the domain wall solution. We wrote down the metric as a sort of warp factor. And we found our Ricci components. So it was pretty straightforward using the Cartan method to find the connection So when we just had a sort of single extra dimension and we had this warp factor times some lower dimensional metric, our computation of the curvature was actually pretty straightforward. And that sort of suggests that we can generalize to a sort of higher dimensional thing by simply bolting together different subspaces that have their own warp factors. So here R has sort of taken the place of Z. Actually, why don't I just keep calling it Z? It might be slightly less confusing. So here I've just sort of said that we've now got this first space, G, which contains time. So I'm going to say this is p-dimensional, and it's 0, 1, etc. So it's a Lorentzian subspace. And this one here is n-dimensional, but it's Euclidean. So it's plus, plus, plus. And this one is plus, minus, minus. So if we just think about what that's saying, it's saying we've got stuff just dependent on something which is kind of the distance from the object. The object is extended, so it's extended in p. Actually, so I don't confuse you, I'm going to say 1 plus p dimensions. And there's also, I mean, although it needn't be, I'm not going to assume that it's like an n-sphere surrounding it. It could be. So if I look here at this black string, just for comparison, here I've got the r as being the coordinate that everything is dependent on. I've then got the z, which would correspond to, although these warp factors are not the same, in this particular case, you can sort of see that this is like a t and a z, and then the two-sphere is what's surrounding it. Or this, you could view this as being a component of 3 separate things. But this is what I'm going to look at just for the moment. I'm not going to go through the computation of the curvature. I'm merely going to sort of highlight the key points, because it's reasonably clear from the way that's kind of split up into nice little boxes that at the connection level, the sort of the mu part of the metric and the alpha part of the metric don't mix. And so we can just really use this here to say what the non-zero connection pieces are.
I'm not really sure I see what the benefit of splitting the metric up like this is.
Because what I want to do is I want to find brane-type solutions. So I'm just at the moment saying that I'm writing something down that is potentially extended, so that's the G part. It's got some extra thing that's surrounding it, that's the Y part, and it only depends on a single coordinate, a single space-like coordinate. So at the moment, I'm saying this, if I had a solution for G and gamma there, then that would be a brane-type solution. Now, whether or not it's a black brane, I don't know till I found the solution. But to find the solution, I need to know the curvature. So at the moment, I'm just computing the curvature so I can then see what solutions I might have. So you're just going to have to ride with it at the moment and then see where it takes us. So if all I'm doing there is really just transferring over what we did when we did the domain wall. And if I then go ahead and compute the curvature two forms, you can see if I'm just focusing on the mu subspace, I'm going to get the same as for the wall. If I'm focusing on the y subspace, I'm going to get the same as the wall, except, of course, it's C, not A. So the only thing that can change is whether there's any cross terms, the mu alpha cross terms. Sorry, alpha hat. So I kind of mangled a bit when I was trying to describe the black string. The black string's kind of an example where there are sort of not just two extra packets or boxes in the metric, there's actually three. But you see that the A prime, C prime, that cropped up when we did the spherically symmetric metric. And it crops up because of the crosstalk between the non-trivial curvature in the time direction and the non-trivial curvature coming from the angular directions. So you kind of go through, you work the whole thing out, and you end up with So what you sort of see when you compute the Riemann tensor is that it sort of seems to split up into things that you can identify. You've got, some of which carry down to Ricci. So you've got curvature that's inherited if either the G metric has Ricci curvature or the gamma metric does. So, for example, if the gamma metric were a metric on a unit n-sphere, this would be something that was constant curvature. It would be proportional to delta. Then you get pieces that are due to that warp factor, the A or the C. So that's this term, these terms here. So this is coming because you've got that space, the G space, which is changing as you move in the Z direction. So that's what these two terms are. And then here you've got this crosstalk. So it's the fact that once you compute the curvature, you actually do get these theta, the gamma-gamma terms or the theta-theta terms. So you get mixing, the crosstalk between those two different subspaces. So, you could add as many building blocks as you wanted. You could add sort of, depends how many dimensions you're in. You can do what you like. But the basic pattern, if your metric only depended, sort of in any real sense, on a single coordinate, you'd get this pattern repeating. You'd get a cross term for each particular subspace, talking to each subspace. You'd get the intrinsic curvature of whatever the subspace was, and then you'd get the curvature due to the warping. So this is like the sort of building block. So at the moment, I'm not really considering rotation, but there's still quite, there's enough interesting stuff even without rotation. So let's just see what, at the moment I got this question about why you're doing it, why this particular form of the metric. So let's use this expression to find the general dimensional Schwarzschild solution. So we're going to find the Schwarzschild solution in d dimensions. So if I want a Schwarzschild solution, that means it's a black hole. So therefore, there's no extra pieces in that g mu nu. It's just a dt squared. So that is my Schwarzschild metric in a slightly different form to what you're used to, but it's the form that I have to do, just translating down from the computation of the curvature I've just done. Here, n is d minus 2, p is 0. But I'd prefer to have this in a form that I'm used to, so I'm going to change gauge. I'm going to set c equal to r, and I'm going to say that dz is dr over b. So that'll bring it into a more familiar form. So if C is R and dz is dr on B, then C prime, which is dc dz, that becomes dr dz, which is B. So that's one thing I need. And C double primed becomes B dB by dr. So there, C double primed is just d by dz of C prime, and d by dz is B d by dr. So now I look at the, remember when we found the Schwarzschild solution, we looked at the 0, 0 component of the Einstein equations. So we'll do the same thing here. So I can rearrange G naught naught, this is what I get, substituting for C prime and C double primed, and the fact that n is d minus 2. But I know that this is 8 pi g T naught naught, possibly plus a lambda. So I'm actually getting exactly the same sort of thing that I had when I found the normal Schwarzschild solution. So if I have a lambda, that's what I get. So here, if, if I look at this, this is just going to be the total sort of energy, at least in a linearized sense, divided by the area of a d minus 2 sphere. Because if I want to find out, sorry, it's also, sure I've got to, no, that's right. Yeah, okay. So if I wanted to find out the total mass, I'd be integrating T0 naught with respect to the full volume, which would be dr times all the angles. And so the integral over the angles just gives me an AD minus 2. So what I end up with is B squared is 1 minus 16 pi g over d minus 2, AD minus 2, m over r to the d minus 3. And then if I have a lambda, then I have this extra term floating around in the end. So d minus 2 is this is the area of S d minus 2. And so if we were in vacuum, if lambda was 0, this would give us the relation between the Schwarzschild mass, the sort of Schwarzschild event horizon radius and the mass. So you see now what was 2gm, you see how it changes with dimension. So you see there's a power of 1 over d minus 3. So previously you had the Schwarzschild radius being directly proportional to m. Now it's proportional to m to some fractional power. And then the prefactors kind of change. But notice that the lambda piece remains proportional to r squared. So lambda is kind of not changing so much. The only thing that's changing is sort of the specific relation between lambda and the ADS or DS length scale. So that's this would become 1 on L squared.
Why is this Schwarzschild radius of B equals 0?
So when B equals 0, that's basically the event horizon. So I haven't gone through to show that B is A, but if you go through the whole of the Einstein equations, you see B is A. And so I just skipped that. I'm just, I mean, at this point, I'm using this intermediate step, which in general, B is not A, right? Because in general, you have some energy momentum there. But I'm using this step to identify the integration constant m. I want to identify what the mass is. So in this case, I'm using, I'm saying, OK, if it was linearized, I would be integrating T0 naught. And as I went outside my mass distribution, this would be what I would call the mass. So I'm just using it, you know, if I didn't have a T0 here, or the lambda, I would just have an integration constant. But I want to know what the mass is because I want to be able to identify this specific integration constant in terms of, you know, exact sort of constants of proportionality to the mass. So that's just saying that the relation between, you know, the curvature scale of the de Sitter or anti-de Sitter is sort of, those are dimension-dependent factors. But it's still essentially lambda goes like 1 and L squared. And so you could have actually predicted that term would not change because the cosmological constant, if you look where it comes in the Einstein equations, it's GAB is lambda, big GAB is lambda, little GAB. And so we know our curvature, our Einstein tensor, which is telling us about curvature has dimensions 1 on L squared. So since the Einstein tensor is always showing up proportional to lambda, that tells us lambda has dimensions 1 on L squared. So we could have therefore guessed that this term would remain as R squared because nothing's happening to change the dimensionality of our lambda. However, if we think about the other term, our Schwarzschild type term, here we've still got a GM, but as we change dimensions, our Newton constant or our gravitational constant changes its dimensionality. So in 4 dimensions it's L squared, in 5 dimensions L cubed, so on and so forth. So, and this shows up in the 1 on R to the D minus 3. So that's sort of showing the difference, if you like, in terms of the dimensionality of mass, of the sort of mass of the object versus the cosmological constant. So that's the uncharged d-dimensional black hole. But now I want to sort of think about charge. Because in 4 dimensions, you have seen the Reissner-Nordström black hole, which is a black hole charged under an electromagnetic, the Maxwell electromagnetic charge. You've also seen that the black hole can be charged with an electric charge or with a magnetic charge. So in some sense, there's this symmetry between electric and magnetic charge, at least from the perspective of black holes. The Reissner-Nordström metric doesn't care whether the charge is electric or magnetic. So what happens if you've got higher dimensions? So, of course, you could always kind of charge your surface, so you could take an electric charge and smear it out, which is, that's okay, you can do that. But then you sort of start to think, well, okay, but how do I know that distribution's going to remain smooth? Maybe it'll start clumping up. You know, what happens if I perturb it, et cetera, et cetera. So is there a different notion of charge which isn't just smeared electric charge? So that's what we're going to explore now. So if we want to just think of a point particle, so we're just sort of thinking classically here, if we want a point particle with charge, we add an extra piece to our Lagrangian, our geodesic equation, which would be coupling the tangent vector to the gauge field A mu. So this will tell us how to modify our geodesic equation. So from that, how might I construct a charged string? So a string is something that is extended in space. So my string now has two directions, a tau and let's say a sigma. So here I've got an x dot mu and an x prime mu. So now I've got two vectors that tell me about the string. So they're parallel to the string world sheet. So this suggests that I have a two-index object that will one index, if you like, for each of those tangent vectors. So how could that be a gauge field? And how can this make sense? Well, if I make B mu nu a two form, then my gauge transformation is that the two form goes to B plus dA, so that my two form has a gauge transformation, just like the gauge transformation for electromagnetism is A goes to A plus d phi, where phi is a scalar. And my field strength is going to be H, which is dB. So this is the analog of the electromagnetic. A goes to A plus d phi, and this is the analog of F is dA. And so now I can see how I might be able to construct general electrically charged objects by simply having, instead of two forms, having p plus 1 forms. So that's at least one way of extending charges and our sort of U1 or our gauge group to higher dimensions by simply extending the notion of what we mean by gauge potential. So we see that the Maxwell gauge potential was very naturally expressed in terms of the language of forms. And so here we're just kind of, supersizing that in a way. But what do we mean, therefore, by a magnetic solution? Well, if I think about what a magnetic solution is for electromagnetism, so let's think about that and work from there. F theta phi was q sine theta. So in other words, our F was q times the sort of unit area form, unit sphere area form. So I take my field strength and I make it sort of a sort of an area form. So that's kind of the notion of what a magnetically charged solution is. So in general, if I keep using this notation H for the moment, H will therefore be proportional to sort of epsilon so our H, am I getting my numbers right? If A has, so if my B has P plus 1 indices, then my H has P plus 2 indices. So that's the area form on a P plus 2 sphere. So you then have to think of that P plus 2 sphere surrounding your sort of black brane, and therefore that means that we've got P plus 2 dimensions surrounding the brane. We've got one dimension, which is the Z or R coordinate, so that's P plus 3. So the dimensionality of this thing is D minus P plus 3. So that's what the dimensionality is. Which is a D minus P plus 4 brane. So it's probably worth digressing a little bit on the terminology here. Back when people were first exploring extended objects, basically there was, although people had spotted, this notion about the sort of the idea of the string world sheet, I guess coming from Reggie trajectories back sort of in the late 60s, early 70s, they couldn't make strings into any sort of sensible theory. So there was some interest, but it was sort of felt to be one of these esoteric subjects. In the meantime, in the 70s, people were also exploring these topological defects, the domain walls and cosmic strings. And so there was a sense in which people were exploring extended objects. It just wasn't the mainstream of particle physics. But then that changed in the early 80s when Mike Green and John Schwarz actually did this sort of anomaly cancellation for the superstring. And so suddenly everyone was interested in strings. And at the same time, it was very natural to think, well, is this something that's special for strings? Or can we do this? Can we make quantum membranes more generally? So you had the sort of set of supergravity people, I guess, working on membranes. But then Paul Townsend wrote this fantastic, it was more the title of the paper was just brilliant. It was super P branes. So at the time, it's like a wall is a membrane, and then they became an M brane rather than membrane, so where M is general, but somehow the P brane is just much more, it's a much more catchy terminology. And so we tend to use P brane as your sort of general extended solution. But brane is just, that gets shortened to brane. So that's why these things are called brane. It's kind of a sort of historical thing. A general brane may be called just a brane or a P brane, But then you've also got d-branes in string theory, which are something very specific, which are the end points. So in string theory, string can have ends. And so usually, initially, people impose Neumann boundary conditions on the ends of the string, so they kind of are free to move. However, again, at the time, there was the realization that, of course, normally when you have a boundary, you put Neumann conditions, you could also alternately put Dirichlet. But again, there was a problem in quantizing strings with Dirichlet conditions at the time. But that was solved in the 90s when it was realized in the mid-90s that actually these d-branes, if you had, again, you were in a special number of dimensions, you could successfully quantize them, but it became this sort of endpoint where these strings ended on, now actually became some sort of physical object, because a string has a sort of charge at the end, so that charge has to go somewhere, and the notion is it kind of spreads out into this, say, plane, but now this plane is itself a physical object, and it can have dynamics. So that's, again, that's sort of the terminology or the difference. So let me just very quickly give an example of a solution. So when you take an effective low-energy gravity theory from string theory, you always get this initial piece, which is coming from the sort of basic excitations or the basic fields that live on the string world sheet. And so this H is, of course, the field strength of the B. So the string always has the B mu nu living on its world sheet. But dependent on what other supersymmetries you ask for, you get this schematic form. I think I've got this the right way around. Do I mean that? One forms. Just trying to remember that I've got this the damn right way around. So. So here, this sort of shows that you can have all sorts of different dimensionality solutions which are charged under either this canonical 2 form or under these additional P form fields. So if we think again, going back to these electric and magnetic solutions, in 4D, both sort of point-like objects, which are zero branes, have both electric and magnetic charges. So that means that if we want, in general dimensions, have a feeling that my basic arithmetic is slightly suspect here, or else P means something different at some point. I'm wondering if maybe I should have put dAp plus 1 in that one, but never mind. So if I'm thinking about something which has both electric and magnetic charge in 10 dimensions, then it has to be a 3-brane. And so this gives the self-dual 3-brane into B, supergravity. So our metric if we put it in our aerial gauge, our Schwarzschild gauge, so our form field F, or H, I don't know, I'll call it F. So it's this sort of quite odd thing that carries both electric and magnetic charge, which are equal in magnitude. So it's a self-dual. If I take the Hodge dual of that form, I get the same thing. And this r plus to the 4th has, in terms of string units, is proportional to the string tension. So it's squared, that's alpha prime squared. GS is the string coupling. And N is the number, sort of the number of these unit charge D3. So remember, we had this notion of when we have a magnetic charge, of it, the charge being quantized. So in a sense, this is sort of a unit charge. Question?
What do you mean by the charges having the same dimensionality?
Well, I mean the object. So like in 4 dimensions, you have a point particle, can be electrically or magnetically charged. If I was in 5 dimensions, my electrically charged, with Einstein-Maxwell theory in 5D, my electrically charged object would still be a point particle because it's still coupling. We've still got that A mu coupled to x dot mu. But the magnetic object would now be a string. Okay. Because it's the F mu nu still has to be proportional to a 2-sphere. So a 2-sphere in 4 spatial dimensions surrounds an extended object. So you kind of have to sort of count, and that's why I say I'm not entirely confident when it comes to simple counting. That somehow always seem to make mistakes. So if I change gauge, if I let rho to the 4th equal r to the 4th minus r plus to the 4th, then I get what would be the more usual expression. So I've written this out in full, sort of to kind of draw, first of all, the analog with the Schwarzschild type metric, where you have one function here, you've got the inverse of the function multiplying the radial coordinate. It's slightly different because now you've got this offset from rho equals 0. So what happens as you go to rho equals 0, which is the event horizon, or would be event horizon, of this object? So let us suppose that n is very large. I'm going to say that 4 pi GSN alpha prime squared is r to the 4th. So I'm going to associate that with the radius. And now I'm going to look at rho much less than r. So if rho is much less than r, I kind of blot out these terms here. So I kind of ignore this term. I ignore this term relative to that on the numerator. So I get rid of those. And then I say, what is my metric, roughly? So hang on, let me do r squared. So if I just look at what I get close in, you see that this is, this now, the S5 has constant radius, and this thing here looks like anti-de Sitter space. So this is AdS5 cross S5. And so this is kind of this was the sort of central solution that people thought about when Maldacena sort of put forward the idea of AdS-CFT. Because this is a D brane, this is a D3 brane. Therefore, from a string theoretic perspective, as a Dirichlet boundary, that means it has if you look at the sort of boundary things living on the boundary, you see you get a field theory in those 3+1 dimensions. If you, on the other hand, look at that D brane as a gravitational solution and look at it when n is very large, so you have the gauge group on the D3 brane is an SUN, then at large n, you see you have roughly AdS5 cross S5. So if the S5 has a constant radius, so you end up with this AdS geometry kind of in some sense being analogous to some field theory in 4 dimensions. So that's sort of, I mean, that's a very heuristic way of describing it, but that was really what was behind this notion of AdS-CFT. This idea that you could look at the same object in 2 different ways.
So is this metric a solution of Einstein's equations in 10 dimensions?
Yes, with that source. Okay. Yeah. So it's just like you solve Reissner-Nordström solution. You know, you find it by taking your either electrically or magnetically charged black hole. You find T mu nu for that given charge, and then you find the solution. So you put in that T mu nu for the charge, and you get the Reissner-Nordström potential. It's the same notion here. You've just got the single, you know, for this vanilla solution, you've got this single gauge field turned on. It's got a particular field strength, which is self-dual, and you find the energy momentum from a gravitational perspective. You find the energy momentum tensor of that, and you solve the Einstein equations. And this is what you get. So the only, just as a sort of last comment, in this solution here, there's a very sort of specific relation between R plus and Q. I think it's Q is R plus to the fourth. And it's what, from the Reissner-Nordström perspective, we'd call an extremal solution. If you do this process of solving the Einstein equations with the energy momentum tensor, just like Reissner-Nordström, you have an integration constant m. Now, if m and q are not specifically charged, there would be r minus terms here as well, so there'd be extra dependence in the metric. So that actually turns out to have something to do with this question of stability. So again, back in the early days of thinking about gravity and string theory, all sorts of extended solutions were being found, and it looked like there was this massive playground of new solutions to play with. However, there's a slight problem with them, which is nicely illustrated with the black string. So I'm going to just think about my black string in a Kaluza-Klein sense, and I'm going to look at a length L of black string. So the mass of this is essentially given by the mass is related to the Schwarzschild radius, and it's also related to the length. So you get this expression for the mass, and then the entropy so it's the area of the string divided by 4g, 5. So that's what I get. The entropy of the black string is proportional to the Schwarzschild radius squared times L, that's the total area, and the Schwarzschild radius squared is proportional to m squared. So now I look at the 5-dimensional Schwarzschild solution. So that's now a black hole with radius r5. So the mass, I use that expression that I had of sort of relating the mass in an arbitrary dimension to the horizon radius. So that's 3, it's d minus 2 times the area of a 3-sphere times of the 5-dimensional radius to the d minus 3, which is squared, divided by 16 pi g5. And then the entropy again, we've got to do the volume now, the area of the 3-sphere. So this now depends on the mass to a different power to 3/2. So now I want to compare the entropies. So I've replaced the r4 squared there with the m squared. So this is just comparing the two entropies. And so if I now square this, or put everything under a square root, I suppose. So here you see that if I make L very big at fixed mass, that's going to make the black hole have a bigger entropy. So from an entropic thermodynamic perspective, if I try and make that string too long and thin, it would prefer to clump into a black hole. So that suggests, the entropy argument suggests that the black string is actually unstable.
Would it only collapse to a black hole, or maybe you could have like multiple black holes like forming in individually?
Yeah. So I'll just finish writing what I need to write, and then. So that's, it suggests an instability, but this is just some dodgy, entropy black hole. Why should we believe this sort of pseudo-quantum gravity stuff? It's suggestive, but in order to show that that actually happens, you have to do some sort of computation. So the first thing is to do a linearized analysis. So tomorrow we'll be looking at perturbation theory and how to do that. And so you calculate little perturbations around the black string space-time, and you indeed find that there is an instability which takes the black string and sort of makes the event horizon kind of wobble. And then just, it's getting to be now nearly sort of, let's say, eight years or so ago, Louis Lehner and Franz Pretorius actually worked, ran a simulation. It took them several months, actually. The code was running. And it sort of depends on the scale you start with. But you're right, if you start with a sufficiently long string, you don't just see one black hole. You kind of see this cascade. It's like a self-similar behavior. You sort of get, say, first of all, it breaks up. It looks like you're getting one bigger black hole inside, and then in the sort of little bits linking this big black hole, you start getting smaller. So you get this cascade of instability. So it seems that, at least in 5 dimensions, so the black string is definitely unstable in 5 dimensions, but it seems like the end point of the instability is that the black string fragments into black holes. And if that is the case, then at the moment of fragmentation, we sort of get an instantaneous naked singularity. So it looks like cosmic censorship is violated in higher dimensions. So anyway,